Hello students, and welcome to the homework part of the nugget concerning systems for efficient use of solid woody biomass in the energy system. Today you might notice that I have a cat here, so if there are noises or if you feel that I am behaving strange, then that is because of the cat. Now, to do this homework, you will have to be well familiar with the basics of how heat pumps work, and you must be oriented in how to set up an overall but simplified energy balance for a system. So the task you shall solve does not require any detailed knowledge on these aspects, but you must be well oriented. As you see from this slide, you are supposed, once you have completed this nugget, to be able to analyze, compare and discuss the advantages and disadvantages with different system solutions to supply a customer, a town or a region with necessary energy services. We will limit ourselves to heating, cooling and electricity, but the reasoning as such is general. We will also limit ourselves to look at only woody biomass, but again, the reasoning as such is generally applicable. To be able to do an analysis like that, you first must be fully aware of the basics of woody biomass supply, and you will find the necessary background in the BusyPlan handbook. Chapters are 2.1, 3.1, 4.1, and you will also find a summary of possible system solutions and technologies in chapter 4.08. You must also feel comfortable with the general properties and function with heat pumps. You do not have to know the details of the thermodynamics, but you must understand the significance and the meaning of the coefficient of performance for heating and for cooling. And of course, you must understand the basics of the function of a heat pump. Finally, you must be able to back-calculate the total demand of resources from the total size of a specific energy system. In case you do not feel fully comfortable with these things, then go back to the relevant nuggets in lesson 3 as suggested in this slide. So let's now have a look at the system we looked at in the theory session in this nugget. Suppose we would have another type of technology to provide the same total service to the customers. You will observe that the Sankey diagram is not to scale now, but I use it only for a qualitative reasoning right now. Say that we would use a hot water boiler to produce the district heating. A hot water boiler should have an efficiency exceeding 90%, but let us assume 90%. So then will the fuel demand to produce the district heating become 48.3 megawatt. Now assume a compressor heat pump with a COP for heating equal to 3.5. This is not a very high value, but it is not unrealistic. The coefficient of performance in cooling applications is then 2.5, and the electricity demand becomes 4 megawatt. So the total need of electricity production becomes 41 megawatt, 4 of which are used internally to provide the district cooling service. We assume the electricity to be produced in a super modern condensing power station using a combined cycle process with integrated gasification and everything. But we still stick to bioenergy. So the electricity generating efficiency is assumed at 55%. The total fuel demand for the electricity production then becomes 74.5 megawatt. So we now have exactly the same output, but the system with the compressor heat pump demands 18% more fuel than the system with the absorption heat pump. Almost 133 megawatt fuel instead of 104 at full load. At part load, assuming 88% boiler efficiency, will the district heating production demand 10 megawatt fuel and the electricity production 32.7. So the total fuel demand at low load is just about the same as with the absorption heat pump. So from a purely technical point of view, you will see that the local system, that is the system where the heat production is combined with the relatively inefficient electricity production in a small scale 104 megawatt thermal plant, is more efficient than a small scale local high efficiency heat production unit combined with a super high efficiency large scale electricity production facility and a compressor heat pump. To arrive at 55% or higher electricity efficiency, the technology in the power plant must be so-called biomass integrated gasification combined cycle, BIGCC, and that requires a large-scale plant. Let us now look at some other aspects of the two systems. First, we will look at the transport and the logistics. The first system can be scaled to fit the heating needs of a smaller city. Viewing it that way, you will understand that the national system, if this philosophy is adopted, will contain many smaller energy plants spread countrywide. That means that each plant will be supplied from a local area, so the transports to each plant will be relatively short. In the second case, will the heating plant and the district cooling production plant be placed in the smaller city? Yes. The location of the power plant will rather be determined either where sufficient cooling can be obtained or where sufficient fuel is available. If the power plant is located where the fuel is, then may hauling distances be minimized, but on the other hand, will there be a demand for a higher total tonnage. So from a total transport viewpoint, this kind of electricity production plant may or may not be advantageous. From a labor force point of view, will the local smaller plant be manned with people working in heat production and in electricity production? So the workforce will need several different competencies and will be diverse. The plant will also be close to the city, so it may become an attractive employer. For the second type of system, will the heating plant be a local facility with a smaller and more homogeneous workforce? So again, it may well be a very attractive place to work. The power station will become more high-tech and may, for that reason, be more attractive for the most skilled workers and engineers. But then it will be placed some other place. There are also secondary effects. With the smaller units, will all the fuel handling be a local affair? So the small cogeneration plant will generate more local spin-off jobs than the local heating plant. On the other hand, will the smaller plant suffer from the common small-scale weaknesses? There will be more labor hour input per energy service produced. And from a strict business economy viewpoint, will this system be less profitable? But then, on the other hand, will the smaller system be more efficient from a resource conservation standpoint? So when dealing with energy system solutions, you may not look away from the societal and the sustainability aspects. The whole idea with a change from fossil fuel to renewable fuel is to make the energy system more sustainable. So then you may not just copy the large-scale fossil fuel thinking and try to force the renewables into that mold. Renewable energy systems need their own layout and they need new thinking. What you shall do now is to look at different combinations of plants and processes to deliver the same energy services to a market. To do that, you shall use the calculation tool provided here in the form of an Excel sheet. To the left are boxes for input data. You will notice that individual data may only be within preset ranges and that if you enter a value outside the allowed range, then the value used will be the end value of the range, upper or lower, depending on your input. The value actually used in the calculation is shown to the right in the box. Further right, outside the boxes, you will see some intermediate calculated values from the input you have given in the corresponding box. The top box is to provide some general data for the fuel and for the boiler. In the second box, you shall enter data for steam pressure and temperature, as well as for the turbine. When you enter the steam pressure, you will notice that the temperature value on the line below changes. The temperature presented there is the boiling point at the pressure you have entered. So the superheating temperature must exceed the boiling point. The treatment of the turbines and the condenser is simplified. Now look at this diagram. Boiling occurs at the boiling point as determined by the pressure. And then there is one more thing set, and that is the condenser temperature. Knowing these two, we also know how the isobar curves look. So the calculation tool uses two fixed points from this diagram. These are the inlet conditions to the high pressure turbine and the outlet conditions from the low pressure turbine. The outlet conditions from the high pressure turbine are determined so that the pressure ratio is the same in both turbines. So the thick red lines in this slide show how the turbines, high pressure and low pressure, are treated. Once you have set pressure, superheater temperature and condenser temperature, are these values computed and displayed in the spreadsheet. You will notice from the slide that the turbines are treated as adiabatic. So there is the option to set a turbine efficiency in the calculation tool. For large turbines, about 100 megawatt or so, may the efficiency today be above 90%, while in small scales, say 10 megawatt or maybe even turbines working with saturated steam, may the efficiency be as low as 50%. You will have to set a realistic value for your calculation. For the heat pumps, you will have to specify if it's an absorption heat pump or a compressor heat pump, and you have to set a value for the COP. For absorption heat pumps, is the COP always less than unity, typically in the range of 0.5 to 0.8. For absorption heat pumps, it is assumed that the electricity demand is 10% of the cooling capacity. This is a high number. For modern compressor heat pumps, are the COP values typically higher than 3. This spreadsheet is the tool you shall use to learn a bit about how systems work. There is now only one thing more I want to tell you. When I was a student, I was surprised to learn that the enthalpy of steam at constant temperature decreased as the pressure increased. As you may remember from the nugget on flame temperature, does the CP value for gases typically increase with temperature? And as you also remember from the nugget about electricity production, does the same thing apply for pressure? So we expect the CP value to increase with pressure, and we expect it to increase with temperature. And basically, we expect the same for liquids. So let us now look at two examples. Heat water from 0 degrees to the boiling point at 70 bar, and then do the same thing at 80 bar. What I've done now is to pick enthalpy values from tables, and then I have back calculated. But what you see is that, just as expected, the mean CP values increase with pressure. Let us now heat the steam from the boiling point to one and the same superheater temperature, and I have just picked 400 degrees for this example. Again, as shown in this slide, you see that the mean CP values for the steam increases just as expected. Adding these two together, heating the water to the boiling point and then heating the steam to 400 degrees now yields that the total energy needed for the temperature rise is less at 70 bars than at 80 bar. So this was what I thought when I was a student would be the behavior. But now enters the third component in the system, and that is the heat of vaporization. At the critical temperature is the heat of vaporization 0. So the heat of vaporization is a monotonous decreasing function of temperature. So the steam formation enthalpy is higher at 70 bar than at 80 bar. And when this is added to the previous numbers, we find that the total enthalpy decreases with a pressure increase at a constant temperature. The reason is that even though, just as expected, the heating itself requires more heat at higher pressure, does the fact that the boiling point approaches the critical temperature reduce the heat of vaporization. And finally, this adds up to the paradox that the steam enthalpy decreases with pressure at a constant temperature. So then you might ask yourself, why do we not plan electricity production units to use high temperature steam at a low pressure? In short, the answer is that it does not pay. At low pressures will the volume flows become huge, and all tubing must be scaled accordingly. The cost increases for this are such that the increase in power output will not cover the cost. So that is why. Now use the spreadsheet to compute some examples in your own neighborhood and consider the market for heating, cooling and electricity. Think about how you would solve the logistics. Where would you put the plant? Would heating or cooling be the most important side product in your region? You're not expected to deliver any report or anything like that. You're only expected to do a number of examples until you feel perfectly comfortable with how a modern CHPC system works, and you have given it a lot of thought so that you really understand the advantages and the disadvantages with big and small different types of production units. You can compare what happens with a compressor heat pump or an absorption heat pump and think around the different system solutions. That's all I demand from you. But I do demand that because otherwise you will not be able to finally fulfill the last examination in this course.